Let's examine the basic differences between direct current and alternating current. First, let's examine DC current. A voltage supply, such as a battery, create current in a circuit that moves in only one direction. Next, let's examine AC current. A voltage supply, such as a wall outlet, supplies an AC voltage. An AC voltage creates alternating current in the circuit. The current alternates in direction. In order to understand how AC is generated, you must first understand the basics of a magnet. A magnet consists of a north and a south pole. Invisible lines of force exist between the north and south pole of a magnet. These invisible lines of force are called flux. Let's look at how magnetic flux is used to create current in an electrical circuit. When a conductor connected to a circuit is moved through the flux lines of a magnetic field, electrical current is produced in the circuit. This is the basic operation of generating electricity. Let's examine the details of this type of electrical generation and the terms associated with generation. One of the factors that determine how much current is produced is the length of the conductor moving through the magnetic flux. To increase the length of the conductor, a coil of the conductor is used. When a coil is moved through the magnetic flux, more current is produced. Let's examine the voltage created in the circuit. To begin, notice that the voltage at the lamp is 0 volts because the coil is outside of the flux lines. As the coil moves toward the center, it cuts more flux lines and stronger flux lines. This results in more voltage being created. As it moves away from the center, the voltage falls until the coil is no longer moving through flux lines. As it moves in the opposite direction, a voltage of opposite polarity is generated. One of the factors that determine the amount of voltage created is the speed at which the coil moves through the flux. Remember that movement has to occur. Placing a static coil in a magnetic field creates no current. The maximum current is created when the coil cuts the flux lines at 90 degrees. When the coil cuts flux lines at less than 90 degrees, a current less than the maximum is created. If the coil's movement is parallel to the flux lines, no current is created. It's impractical to generate current with a horizontal, that is, back and forth movement. A circular movement is more practical and efficient. Notice in the example, the coil cuts through the magnetic flux lines in a circular motion. Notice also in the example the voltage created at the light bulb. The voltage goes from a maximum positive voltage to a maximum negative voltage. This is the basics of a generator creating AC voltage. Let's examine the voltage created in one revolution of a generator. In this example, 4 points are identified in one complete rotation. Let's begin by examining the voltage created from point A to point B. At point A, the coil is moving in parallel with the flux lines, thus no current is created. As the coil moves to point B, the coil cuts the most dense flux lines. At point B, the coil is cutting the flux lines at 90 degrees and creates the maximum voltage. At point B, the coil is cutting the flux lines at 90 degrees and creates the maximum voltage. At point C, the coil is moving in parallel with the flux lines, thus no current is created. At point C, the voltage at the load is 0. At point C, the coil is moving in parallel with the flux lines, thus no current is created. As the coil moves to point D, the coil cuts the most dense flux lines. At point D, the coil is cutting the flux lines at 90 degrees and creates the maximum voltage in the opposite polarity. As the coil returns to point A and completes one revolution, the voltage falls back to 0 volts at the load. With each revolution, the generator produces a voltage that rises and falls and changes polarity. A coil must move through a magnetic field to produce current. The coil can move while the magnet is stationary, or the magnet can move while the coil is stationary. In the example shown, the coil is stationary while the magnet is rotated. This method of generating current is the most common method of generation. This method creates the same AC voltage. A voltage time graph can be made to see the relationship between the voltage generated and the time at which the voltage is produced. Notice in the example that as the coil begins to cut dense and strong flux lines, the voltage rises to its maximum. As the magnet continues to rotate, the coil cuts fewer and weaker flux lines and the voltage returns to zero. The voltage produced in the second half of the rotation produces a voltage that rises and falls in the opposite polarity. One complete cycle produces a sine wave. A sine wave is a graphic representation of the voltage on a time scale. The term cycle is used to identify the voltage created by a complete rotation of the generator. The term frequency is used to identify how many of these cycles occur in 1 second. The term hertz or CPS is used to identify a frequency. Notice in the example how the different rotation speeds create different frequencies. The term time is used to identify how long it takes to complete one cycle. A time expression is used to identify how long it takes for one complete rotation of the generator. Time, as it relates to frequency, is expressed in seconds. Alternating current is created by moving a coil of wire through magnetic flux. Flux are the invisible lines of force created by a magnet. The term frequency is used to describe the number of times that a generator revolves in 1 second. The term time is used to describe the time necessary for the generator to produce one sine wave. Generators, and the AC power that they produce are a vital part of the electrical industry.